Hi, everybody. Welcome. In less than a minute, we are going to kick off, so stay tuned. Okay, so hi, everybody, and thank you for joining our fifth session in the AI for Pathology summer school. So we've been through the first four meetings discussing the general principles of deep learning. Then we discussed the classical deep learning architectures such as UNet, like the usual convolutional neural networks. Then we talked about the journey from RNNs, LSTMs to a transformer, which lend the foundation to foundation models. And this was the topic of our previous session. And today we are going to talk about the next and I would say current frontier in AI, which is also alive and kicking in computational pathology, which is agentic AI. And this is a very, very exciting topic, and I hope you will enjoy this session. And as always, happy to try to answer any questions, and let's get started. So let me share my screen. Let's see. Okay, this is the screen. Okay, and now I go to the, okay. So, agentic AI in computational pathology, from reactive image analysis to autonomous research and diagnostic partners. So, this is a very, very, I would say, good subtitle, as it really captures the transition that we are experiencing with agentic AI. Now, when we look at the evolution of pathology AI, of AI in pathology, then the first wave was, I think, what we've seen from 2016 until probably 2000 and probably 22, 23, where we really were busy on using the classical computational neural networks. The tasks were very well specified. We want to find, I don't know, PDL1 cells. We want to find tumor cells. We want to find cells that responded to Ki-67. We want to predict patient outcome. So very, very, very specific task. Usually it required manual annotation and also manual supervision. So the person, the expert, is super important in the loop. By the way, the expert, the human expert, is important in the loop. This is something which I think is not changing, but also in classical neural networks, in the wave one, the expert also had to do a lot of work. Okay, so it's not only to supervise, but really to work. Now, since I would say 2023, so for the last 3 years, we see how foundation models are really entering the field of pathology, healthcare, and I think this is super, super exciting because so a lot of, and we discussed it the last time, a lot of foundation models in pathology are relying on visual transformers and also foundation models for computer vision in general, being it Dino or SEM 1, 2, 3. So these are used to create a foundation model which gives us a very good representation of pathology data, and hence you can take this representation and derive from it a lot of downstream tasks. So it gives you a benefit that the representation of the data is much, much wider and more comprehensive than it is for the classical computational neural networks. And this is still a very, very, I would say, interesting field, evolving. And I think that I would say the challenge, the way that we see it, because we are not, in DeePathology, we are not, creators of foundation models. We are users of foundation models to enhance the experience of annotation as well as the experience of detection. The third wave, which is the topic of the discussion today, is that of agentic AI. And I know there is a typo here, and I left it on purpose because, as you can imagine, I'm also a user of AI. So I'm creating a lot of visuals and text, etc., together with AI. And I always like to keep an eye and see that it is good. So even if I co-created it with AI, I want to make sure that I read and understand and agree with everything that Claude or Gemini or ChatGPT actually suggested me. And here I kept this typo because I think is a very good example to represent how all of these tools are prone to silly, misleading mistakes. And I think that this is one thing which is very important also for agents. At some point, you have to realize that you, as being part of the team, and the team can be AI plus humans, you are a super important, I would say, participant and manager and supervisor, because the only actual intelligent creature in this team would be you. I don't like the term artificial intelligence. I think it's artificial reasoning, artificial copy pasting, artificial composing. I still believe in human intelligence. This is like a side note. So in agentic AI, the idea is that we are not merely having input and providing output, and the output could be detection, segmentation, or any, I would say, statement. But here we have, I would say, some kind of a flow of actions, decisions that can be done by the agent. So it means that the agent is provided with a goal. This goal leads to planning, to approaching tools, to use tools of short and long-term memory in order to provide reasoning and come out with the result. And we want to understand today how this thing is working. And so the first thing, why is it, how did agentic AI emerge? So it did not emerge as, like in foundation models and transformers, there was like this epic paper of attention is all you need. Here, it's not really the same process. I think that a lot of people starting thinking in this direction, and actually the term of agentic AI was coined by, I forgot the name. Oh my God, how did I will remember or not. So it's really, I would say, culmination of a lot of efforts. Now, what are the limitations of what we may consider as reactive AI? And the limitations are usually we are looking at a single step inference, which means that we have a prompt or some kind of image, and we get a static prediction. And this static prediction can be sales or reporting or outcome prediction, whatever. It does not give us some kind of multi-step reasoning or some creation of some flow or dynamics of some kind of a workflow. The second thing is that when we look at deep learning algorithms, we really need to tune things by humans. The humans, us, needs to really adjust our the parameters or adjust the prompt we are using. We have to refine things. So there's a lot of work, and basically we do see it when we look at for example, the creation of AI solutions with our own platform. There is a lot of fine tuning, which up until now was done manually. Also, in the context of pathology, when we developed an algorithm, and the algorithm is was trained on clean, good samples, and somehow we get some artifacts resulting from staining or some scanning artifacts, etc., then the algorithm would fail. And we don't, I mean, we expect it to fail. We don't expect it to recover itself and to reason, okay, in this area, I'm going to fail. It will just fail. And so we don't expect this to, we don't expect this to be reasoned by the algorithm itself. And also, the process itself is composed of isolated operations. There is no one entity which composes an entire process of this thing. So when we look at the limitations of traditional deep learning, then the main differences when it comes to agentic AI is that of autonomy, of the ability to reason, to look at what happened in the past, or to have some kind of memory, and also very important to interact with tools, to call via APIs, to call functionalities which can do things. So understand what you have to do, and then be able to call upon tools, get the feedback of the tools, involve it in the process, so to create some kind of a multi-step process. And the human in the loop is still important, but not as someone who has, let's say, to tune parameters, but as someone who has to really look at the entire process and make sure that it makes sense, that the agent was not rewarded, and we'll explain this term immediately, that the agent was not rewarded for doing stupid things, because it is, and you will see when we deal with how you train an agent, that it's really, giving a candy to someone who's doing the right things, and this is and you have to make sure that you gave the candies when things were really done properly, because this is super important. Now, when we look at the agentic cognitive architecture, we have a whole, I would say, set of actions in the process, where the first thing would be to sense the world. Okay, in order to do things, we have to acquire or get some data. This data can be visual information, text prompts, anything which will tell us something about the world. Once we have this data, then the agent would have some kind of task to do, some objective that it has to do with the data. And this is the process of the planning. So the planning would be to deconstruct the high-level objective into tasks. And this is, for example, can be done by an LLM that will go and say, we need to measure something. What do I have to do? And then, the LLM will tell you have to do this, and this. So it's some kind of a reasoning which is based on LLM training. And then the next thing would be to translate the set of activities into actual using of tools. So let's say I want to quantify the number of Ki-67 positive cells. So the first thing would be you have to take a digital slide, then you have to divide it into tiles. In each tile, you have to find a Ki-67, you have to apply a Ki-67 detector, and then you have to take the number of cells and you have to generate a report, okay? So in order to, for example, deploy some kind of a Ki-67 detector, then the agent would know that it has to call a cell detection algorithm. Okay, so this is how the higher level task is translated into subtasks, and each subtask may have some kind of using tools. Now, why do you need the memory? You might need memory because, for example, you want to have some kind of report which will I would say gives you some I don't know, thresholds, or will maybe in a specific type of slides from a specific scanner you need to do pre-calculation or something. So the agent will always be able to get access to this memory and be prompt to handle situations or to generate the desired result. So it's some kind of a knowledge-based that is available for the agent. And eventually there would be some action. Okay, so there is the sensing, then the thinking, and then the action would be to execute things or to provide an output. And then you get the data again, and you go over and over again. So rather than just me giving some prompt or pushing a specific button or doing annotations and deploying an algorithm, an agent can do it for me. So I can say, find the yellow cells, and the yellow cells will be found just by giving a text prompt or something like that. So this will be translated into an action. I hope to show you something like that in our 8 meetings, so stay tuned. So trying to summarize everything together. So the agent is composed of some kind of a brain. And this brain is actually the controller that interprets all the things and initiates everything. Then there is the planning and the composition into sub-task layer, the tool, an action layer, which is very important. This is the part where you know which algorithms you can use and which APIs are available for you. There is the memory layer and some kind of a workflow guardrails layer, which actually handles all the, I would say, safety and security issues, stops when it says, okay, I need a human in the loop, I need the human to sign it off, I prepared everything, now please, the expert pathologist, you have to make your decision. So all of these layers are working together to provide, I would say, an entire interactive and active and semi-autonomous system. Now, let's give some examples, some possible examples for autonomous whole slide image agent. So for example, let's say that we want to to look at slides in more or less the same way that a pathologist looks at slides. So in a first glance, let's say that I want to just be able to know where the tissue is in my slide. Because if I want to deploy some kind of a cell detector, it doesn't make sense that I will do that on the empty part of the slide. So an agent might say, okay, the first, I want to count the number of cells. So I will first go into a low magnification overview, look at the entire slide in the low level magnification, determine the boundaries of the tissue. Once these are determined, I'm going to apply anything, and maybe I will also use this low magnification overview to find artifacts, etc. So autonomously, we will replicate what pathologists are doing anyway. Another thing that an agent may do, let's say that I want to do some features extraction, and these features extraction can be from spatial analysis to I don't know, to measuring the size and the intensity of cells, etc. But then the agent, rather than the, let's say, user trying to say which are the safe areas that have no artifact, then the agent will do that as part of the process. So it will be like I would say a series of actions that the agent will do autonomously as part of the process. Another example is like a multi-modal staging, which means that it's not like you have only a single, isolated task, but it could be that the agent, in order to provide a comprehensive report, would have, after zooming into the tissue, after getting rid or correcting artifacts, it will, run one algorithm by the other in order to provide a full comprehensive report. Okay, so all of this sounds pretty neat and very, very interesting. But we talked a lot in the previous 4 sessions on how AI architectures look like and how you train them, and we all remember the forward pass in the neural network, and then the back propagation, that we need a ground truth, and we have a loss function, etc. But this is here more complicated. This is here because we are not talking about input, output, and just generate the right output when you get the input, but we have here an entire trajectory, an entire path, route of actions, and it's not like standard fine-tuning when you have like pairs in LLM, when you have a pairs of question answers. Here we have a sequence of operations, and it's really here, for example, if the user goal is to analyze the whole slide image for regional cellular anomalies and quantify tumor infiltrating lymphocyte, which is a very common task, then the agent will have to break this statement into tasks and decide which tools to call, like feature extractor or segmentation model. And then once it receives the output, it will have to create some kind of a response. So so how do you make this entire list? How do you train an agent to do that? So the idea is that you are actually fine-tuning LLMs large language models to be able to create this division into tasks. So the idea is that you will have like a very powerful general purpose foundation LLM, and this could be really, like ChatGPT or Claude or Gemini or any other thing. And then this model, the LLM model, is further fed with the training data. And the training data will be consisting hundreds or even thousands of examples of how experts solve workflows. So it means if I have a task, then I will have an example of how this task is actually, I would say, divided into subtasks. And this is how I can really train my LLM to learn this, I would say, generation of the flow. And again, the idea is the same. We have an input, we have an output, which is a sequence of commands or of operations. And again, what we want to do is to minimize the loss function over this multi-step trajectories. And this is how the model learns how you do that. What would be the syntax? What would be the logical flow in order to attend to a complex tasks? And as always, we don't want our training process to to go into dead ends or to start hallucinating, which I have to say that hallucination is really something that you still see with even when you use the larger language models. You have to be careful and to make sure they are not just telling you nonsense. And this is why we have always to keep an eye and don't believe whatever your LLM tells you. It's the LLM, if eventually, it's a it's really it's something that we see even our I would say personal dynamics, that we are consulting with our LLMs, and I think you really have to be critical. But now let's keep in mind that we are continuing to be critical. We are not believers of LLMs. Now, the what we call supervised fine-tuning for agentic workflow is to provide the model, the agentic workflow, to provide not the ground truth, but this, here we call it golden demonstrations. And the golden demonstrations actually provides the agent with the gold standard for the how it should think, how it should loop, how it should call tools, and arrive into a conclusion. And we need we need to have these to provide the agent with some, I would say, good practices on how to do things, rather than let the agent just learn by trial and error. And learning by trial and error is very, very strong. And in this context, maybe you've heard of the term reinforcement learning. Reinforcement learning is a learning process where you are getting rewarded for good behavior in a way. So in a way, you are going to try a lot of things. Where you made mistakes, you will not be rewarded. And when you're doing good things, then you will be rewarded. The problem is that when you are looking at a like multi-step sequence, and you allow trial and error, it makes sense that you will make a lot of errors before you accidentally stumble into the right way to behave. So before we are using a mechanism of rewarding the reinforcement learning, we want to give some best practices so that among best practices, we will find the best ways to achieve things. Okay, so trial and error is not a bad approach, but it really takes time, and it can generate super unwanted behavior that maybe we can avoid altogether. Now, how do we create this gold standard? So the gold standard can come from the humans. So and this is of course can be very high accuracy, and can be in great alignment with what humans would do. But so basically we are taking professionals to provide annotations where these annotations are not merely, limiting the boundaries of cell, but the annotator, but the concept is the same. You are going to annotate to provide the ground truth to a complex, you are given a complex goal, and you want to say, I'm going to do this, write code, call this tool, and then I'm going to create an output, and I'm going to correct my error. So we are going to generate the ground truth by the user, and we are really recording all the activities of the human user, and so everything is, you have a goal, you have a complex set of operations that the user is doing, and this is recorded as the desired outcome of translating this objective into a set of actions. Now, this is very good, but it's super time consuming, super complex. It needs a lot of interaction with humans, and it's not bad, but it's, even for pathology, even for creating a cell detection algorithm, it requires really a lot of time. So let alone having humans provide set of actions. So what else can you do to train a neural network? So the next thing that you can do is to use methods which deal with rewards. So the idea is we are looking at possible responses of the system. So let's say we give the system a task, and we see what's the process that the system suggests. This could be an LLM. And then we are going to have human evaluators rank the different model outputs. So we have humans that are saying, this is a good approach, this is a bad approach, etc. And we are training a reward model to mimic these the human preferences. So we have the model output, we have the ranking of the human, and then we are training immediately from the model output to the ranking of the human. We want to provide an AI model via reinforcement learning to maximize the reward. And reinforcement learning means that we are creating a mechanism that rewards our algorithm for good behavior and does not reward it for bad behavior. Now, then we can really create a loss function that will simply divide the actions into a preferred versus rejected in a way, So some kind of a classical classification model to adjust the model. So the idea is that we are going to translate the human feedback into a mathematical reward system that will learn what is a behavior that should be rewarded. Okay, so the AI agent is getting a reward for doing what we expect it to do. Now, let's dwell a little bit into reinforcement learning. This is a term that we did not touch yet in the previous lectures. And here we want to see how to optime the behavior of agents when it interacts with the environment. Now, the reinforcement learning agent is learning through trial and error. So you remember, first, we have this supervised learning with the gold standard because we don't want the agents, to work around to be completely knowledgeless. Okay, we want it to concentrate on, I would say, some kind of a space of activities which make sense. And among these activities in the space that makes sense, we want to make sure that the agent is taking some action, execute it, and then within this trial, it either gets a reward, and this reward can be either positive or negative, and then it learns how to really navigate in this space. Now, the idea is that when the agent tries over and over and over again, it aims to maximize its cumulative reward over time. So and this is like a critical point. The idea is not to memorize the actions, because to memorize the actions would be similar to what we know in machine learning and in deep learning as overfitting. We don't want our agent to overfit our examples. We want our agent to learn strategy. And again, how do you avoid falling into overfitting, falling into memorizing data? The trick, as usual, is diversity. Okay, and diversity means that we need to look at a lot of possibilities at a larger space, because if you can really, I mean, it's perfectly okay to have like a sequence of actions which are really, if you do this, then you do that, and if you did this, and this is a deterministic approach, and it's perfectly okay. And for some tasks, you don't need more than that. But the whole thing is that you want the agent to learn structure of reasonable activities. So when it has to address, I would say, a somewhat different tasks, it will not be completely clueless, but it will know what strategy to use. I mean, and the ability to do that is not trivial. Is not trivial because it is much easier to to collapse into the memorizing data approach rather than really having an agent. And I can tell you, I'm a customer of, I don't know, of airlines, of credit cards, of, I don't know, of I don't know, anything. And a lot of times nowadays, I'm not talking to a human, but I'm talking to a chatbot or to a chat phone, and I have to say, at some point, I'm like, I'm telling myself, because I'm trying not to be rude to chatbots. I try not to be rude to humans, but I really say, oh my God, it doesn't understand me because I need to ask something which is not in the workflow. It's a little bit, it's a little bit niche. It's a little bit like unique question, and I have to say that most of the problems I have, which are not merely asking for info, but something which is a bit more complex, I always wait for the human. I always wait for the human because I haven't dealt up until now with a chat bot or any bot which could really help me in more delicate problems. So again, this is an evolving field. We need to be careful, even when we try to teach strategy. It's still a artificial intelligence. Okay. I think it's a bit strange that for someone who's dealing with artificial intelligence to be so critical on artificial intelligence, but I am critical. I'm critical because I think that you need to know what you can do and you need to do what the limitations are. And once you are aware of the limitations, I think that you can really make more profound and significant use of artificial intelligence. Okay, so we talked about the training of AI agents, and one was the reinforcement learning, and the other one is the DPO, the direct preference optimization, and I want to also spend a few minutes on that. So the idea here is to do something which is again reward the agent for what human would prefer to do, but we want to do it a bit simpler. So the usual rewarding model can be very strong, but it is super expensive from computational point of view, and it's unstable. So what we want to do is to maybe bypass the reward model, and you are trying to really express the reward in terms of the language models output probabilities. Now, what does it mean? It means that we are providing the training algorithm with the pairs of responses generated by the model for the same prompt. So we have some prompt and we have pairs of responses, and there is always the preferred response, so it's the better one, or the rejected. So, and I don't know if you, for example, if you are ChatGPT users, you could really see this approach in action, because sometimes you get from ChatGPT 2 responses, and they actually ask you which response do you like better. Now, they don't ask you about specific word, they ask you about the entire context because they present it in a separate way. And this is, in a way, the way that we are contributing to the DPO of ChatGPT. Now, this is so then the DPO mechanism is training to get, I would say, to create a loss function that would prefer the better response, the preferred response, rather than the rejected response. So we are giving two options, and we want to compare which is the preferred option. This really another mechanism to find the best course of action for an agent, and it provides a stability, a efficiency, and again, it safeguards you and it safeguards the algorithm when you look at an entire workflow. Okay. So as you can see, the training of AI agents is complex. It's more complex than having the static reactive type of any, I would say, classical neural network algorithm. Now, another thing is the agent has the ability to actually try to assess different courses of action before it decides what to do. So, for example, if you want to plan something, yes, and you take notes and you say, okay, so let's say I want to go on vacation. Well, should I go to the Caribbean? Should I go to Norway? Should I go to Italy? And then you write the pros and cons and how much it will cost me and flight time, etc., and the weather. And so you are meditating your, I would say, desired vacation, and this is how you can, simulate it and say, okay, I'm looking at this information, this would be my preferred course of action. And this is something which is also being done by agents. It's called reflection, and when so what reflection does, it provides some kind of a verbal reinforcement loop, which means that the agent is getting an input, tries to see that it makes sense, if there are any errors, and then it could try again. So how does it work? So let's say that the agent is calling some pathology microservice or anything that it wants to do, then it will receive some feedback. Maybe it gets the results and there is some error in the result. Maybe it gets a notification there is a missing a parameter. So in general, it can also encounter problems. Rather than break under the problems, then the agent is trying to correct the problem. So try to imagine the agent got an input, produces some kind of an action. The action fails. The failure is brought to the attention of the agent, and then the agent tries to realize, also an LLM-based approach, I got this error. Why did I get this error? And then the LLM can explain why it got its error. And this is like kept also in memory in order to improve for next time. Maybe it can do some kind of correction. So it's not really intelligence, but again, it learns from mistakes. And I think learning from mistakes is maybe one of the definitions of intelligence, that you are not only that you are doing mistakes, but you can learn and correct your mistakes. And this is, I think, something, the reflection is very, very strong and important, because it's trial and error and learning from your errors. And not only that, but you can use, if you want to predict what would be the best trajectory, then the agent is also able to build, as I said before, different routes in a decision tree of possible actions. And then it explores, I would say, different paths to do things. And then it can assess the result of using the different paths and see how well the results it got from every path. And of course, you need also to set some kind of a metric to assess that. And then the best paths, after assessing several paths, would be kept as a strategy that or a policy that the agent can use for a future actions. Okay, so I will go to skip that. I think that I want to skip that because I think that the issue on how you train agents is super important, but I think that you got, I hope you got the main idea, and I want to move further a bit into pathology. So let's see, I'm going to skip that, and okay. And so I want to spend the time we have left and exploring a little bit on agents in computational pathology. I'm not going to talk about all that is out there. It's not like a review, but it's just giving you some notable examples. So my first example is again coming from Mahmoud's lab, where they actually presented SlideSeq. So SlideSeq is built on what is called PathChat Plus. So PathChat is like ChatGPT that was retrained for pathology, and it uses agentic exploration to navigate all slide images. So what you want to do that, the agent is provided with a task, and the task would tell the agent what is the tissue, the patient, some information about the patient, review these region of interests from the histology slides, and provide the most likely primary diagnosis, and suggest two other possibilities to consider. And so basically, we are not annotating anything. We are not, providing something super specific like we used to do, but we provide a task, and the task is translated. So the side is this task is translated by the agent. So from the text, okay, there is like course of activities. Okay, I want to give diagnosis. In order to give this diagnosis, I have to deploy a cell detector, I have to deploy a tissue detector, I have to count the number of cells, etc., etc. So the agent is applying autonomously, without me having to do that, a set of tools, and this set of tools will eventually provide us as output the primary diagnosis and also other possibilities. And this and we always have to when I guess that when Mahmoud Labs guys and girls were training SlideSeq, then these results were I would say verified, and when there were errors, these errors were used to create a better prediction models. And this is different from I would say the single task, narrow approach that it was the primary approach up until now, where you are taking a task and all the work is being done automatically by a set of agents for you. Another famous, I would say, biology agent is K-Pro by Okin. It's so Okin K-Pro is a agentic platform designed for biopharma and life sciences research in general, but it also has specific utilities for a pathology. For example, it relies on basic tools like cell segmentation and classification. Usually, having cell detectors, cell classification is like, I would say, getting the raw data out of the slide. Then, upon that, there is a spatial tumor analysis that they provide. Again, it's a set of tools. But the thing is that based on these tools, which I mean, cell detection, cell classification, I mean, okay, anybody does that, even us do that, okay. But and the spatial analysis, this is also something. Once you have the cells, it's pretty easy to generate a spatial analysis. But they also integrated this with Claude, which means that you can ask the K-Pro system to do analysis for you. So find me the spatial distribution of tumor cells within some tissue. So this means that this will initiate, again, this will be, like we saw before, this will be divided into subtasks, and these subtasks will eventually be translated into applying a cell detector, applying a tissue segmentor, and then doing the spatial analysis, so relying on lower level tools, but being able to translate the command into set of activities and being able to deploy them and create the result autonomously. The last tool that I want to discuss would be AIStat by PathAI. The PathAI agent is also is using some kind of prompt for the user. The agent then creates a plan to achieve what the user is asking, and again, using the tools. These tools are deployed to get data from the slide, and then the agent can analyze the data and provide the report. So these are just a few examples of what you can see today. I think that this is really fascinating, and I believe that such capabilities will be more and more available in all AI platforms for pathology. So one of the, I would say, things that are super nice is the PathChat, and the PathChat is really take a ChatGPT and retrain it on pathology data, which is really super amazing. So when we, oh, I'm sorry, okay. So it seems that agents are really finding or paving the way into a preliminary overview of doing QC and the QA of slides, doing some diagnostic analysis autonomously, and also drafting reports. I think that in every part of these agents have a really a superb, very, very important role. I think that the agentic, different agents have different behaviors. I believe that agents have capabilities which really depend on how much information you give the agents, and how much supervision is required to make sure that the agents are not doing any harm. Before we close the hour, I believe that the most important thing, while agents and AI in pathology is really rapidly advancing, we still have to primarily consider reliability and safety of what we are doing. We have to adhere to regulatory frameworks because we don't want our agents to guide us into doing things which are wrong. And still, we need the clinician, we need the human investigator, the human researcher to make sure that there are no, I would say, hallucinations in what agents are doing. I think that we are really in the beginning of a fascinating area where we have agents which are doing specific jobs, and as a team, they are doing collaborative work, being able to use active learning to learn from mistakes and to audit themselves. So we want the agents to really make sure that they are doing the right things. I think that this would lead to more trust and more usage of agent. And yeah, and I'm also happy to say that we are also adjusting and bringing in agents into our own workflows slowly, carefully, but this is definitely part of the future. So yeah, I'm not going to go into the risk. I think that I've discussed it in details through the presentation. I want to thank you. So we reached the top of the hour. I want to thank you for the time spent here with me. Next week, we are going to talk about, we are going to review a decade of AI in pathology. So I'm going to just go over, I would say, some research and some works that have been done. So and to show you also the progress and to show you what was done in the last decade, more or less. And then in the lecture after that, we are going to talk about, I would say, systems in pathology which represent the state of the art of what can be done today. So have a nice evening. Thank you very much, Sindhu. Thank you very much, Jacek. Always good to see you here. My God, I hope it's not too late for you down there. And I wish you a nice morning, afternoon, evening, or night, wherever you are. Thank you very much. Bye-bye.